Welcome everybody. It's nice to see you. So today we are very, it's my great pleasure to have Dr. Ding here to give us a talk on his recent work. So a brief introduction to Dr. Ding. Dr. Ding is an assistant professor in the statistics department at the University of Minnesota. He's also affiliated with the ECE department. And before that, he obtained his PhD degree in engineering science from the Harvard University. And then he worked as a postdoc fellow at the Duke University. Dr. Ding's research focus is on foundational principles and new methodologies in machine learning. And specifically, he's focusing on collaborative AI, privacy, and online streaming data. So today he will give a talk about privacy-sensitive collaborations through assisted learning. So this will lead a new research direction in machine learning to enable agents to assist each other and at the same time to keep their privacy. So Jie, you can go ahead.
Thank you, Yi. So this talk is about privacy-sensitive collaborations through assisted learning, which I'm going to introduce more later. So first of all, it's my great pleasure to see all of you here, and it's and this is a joint work with my collaborators, including Yi and Yu here. So it's really my great pleasure to see all of you here, and this motivation comes from the Internet of Things when our lives are surrounded by different sensors, recording our health data, traveling data, and many other aspects. So we are surrounded by machine learning services. Inevitably, we are surrounded by information exchange and some level of privacy leakage. So in general, we prefer to have some service that doesn't compromise our privacy. This is one motivation. So another related motivation is this vulnerability of personal identity. So there has been a recent study that showed that studied several large data sets, and they showed that 99%, 98% of the Americans can be correctly identified from these data sets, from each of the data sets, even if their identity is denominalized. So we don't have their name and security number, but we can still recover who they are from only 15 features. So these features include, for example, zip codes, date of birth, gender, and so on. So the study basically shows that it's very easy to get our private information leaked. And this privacy is an emerging issue, not only in terms of ethics, but also regulations. So there has been a growing public awareness of this concern, of privacy concerns. So for example, in a recent headline news, the data broker Experian sold a large data set that contains 248 attributes. So this is much larger than 15 attributes of 120 million Americans. And also, there is another news that we probably heard 2 years ago, that the Facebook users' personal data were leaked through some third-party app. So this will cause some, this caused a lot of social concerns. And because of these events, these kind of events, there have been different regulations global-wise, including the most recent California CCPA regulation last year, a few months ago. So this regulation restricts the way that companies sell and utilize users' data. And also, from the product perspective, people tend to prefer products products that respect privacy, not only about the functionality. And also, another context that is also related is this so-called machine learning as a service. So this machine learning as a service deals with different entities, like different companies, different government agencies, each of them having private data. And they will work with each other to come up with a joint solution or to improve their services through this so-called machine learning as a service cloud platforms. And AWS is one of them. So during these collaborations among different entities, there is this possibility of leaking model information. It's not only a matter of data, it's also a matter of private models. So people may, so adversaries may be interested in what other people are doing through these platforms, and business will probably also concerned about their model privacy and objective privacy. So the privacy is in general, by the dictionary, is in general the state of being free from public attention. In our context, we may think it as a state of keeping certain knowledge from adversary. So in this machine learning setting, typically our knowledge is about personal data, models, or objectives. So for example, my traveling schedule, or whether I went to a particular clinic. So this is about data privacy. And the learned model implemented on the back end, or my competitors' recommender system. So these are about model privacy. And also, what is the other team or my competitor trying to do with this data? So this is about objective privacy. So there are different aspects. And this privacy sensitive machine learning, the general area or general direction is to study different strategies to guarantee a certain kind of privacy. So this privacy has to be defined on case-by-case basis, because it depends on the adversary or threat model. So for example, if the adversary already knows everything about us, then we can do nothing to prevent our privacy, to preserve our privacy. So it really depends on the setting. But there is one thing that is kind of understandable. So that is, we prefer not to share our sensitive knowledge with others from day one. So if our data is always privately stored in a local server or local computer, it's safer than transferring them or sharing them through the public channels. So it's preferable not to share the sensitive knowledge from the beginning. And this has motivated different learning frameworks recently, including this federated learning and assisted learning, which I'm going to talk a little bit more. And this also motivated different privacy frameworks, such as differential privacy, and some other privacy framework that I am also developing, but I will not mention too much today. So today I'm going to focus on assisted learning, and I will first introduce general notion, general motivations, and also some application scenarios. And then I will move to different methods from different perspectives. So the assisted learning was originally motivated by the human intelligence. So we thought about human intelligence when they help each other with their unique data and skills, and to help each other with their personalized goals and private knowledge or private experience. So people tend to talk with each other without telling everything about their life details, but still can do a good job together and create novelty. So this is general motivation. And we think AI should be able to do the same in general. So AI should be able to network with their resources, data model, or computation, and assist each other's personalized goals. So in doing a particular machine learning job, they send a particular information instead of all of them. And one potential application scenario is to consider the local business, say local ice cream shops, local malls, shopping malls, or local banks who serve the same underlying population. They have the data of similar nature, say data collected from the same cohort of residents, but they are not going to share it. They are going to work out a way that they can do things together. And the smart cameras, like 2 different cameras installed in the same room, observing the same objects or installed in the same street. So they want to recognize objects collaboratively without sending the raw images to each other, because that is also resource consuming, time consuming. And also cloud service that provides different companies with their customized services. Say cloud-based companies who provide services to different small business who uploaded their data, but who will not share their data with potential competitors. And also different trading companies who target the same market, but maybe with different purposes. And the data here is not an issue. Data privacy is not an issue. So what is the issue here is model privacy. So in general, we consider the following scenario. We start with the setting where we have 2 entities, say 2 companies or 2 divisions within the same company. So they are equipped with their private data, models, or tasks. And they observe the same underlying objects, for example, mobile users, residents, patients, and so on. And these objects can be uniquely identified by some index, say data ID or username, nickname, and so on. And we consider the supervised learning scenario where agent B, entity B will assist A. And we will talk different extensions later on. So here are some examples I just mentioned about A and B. So the general goal here is to allow entity A, to improve its learning capability without transmitting the private information from A and B. So we will need to transmit something, and this something is going to be not raw data. It's going to be calculated, some calculated statistics. And 2 characteristics of this assisted learning are going to be autonomy and privacy. So autonomy here means we do not need to pour all the data into a center. We don't need a central controller to organize everything. So it's going to be fully decentralized. And the second is about privacy, where we are not going to share private local data or models or even learning objectives. So no one knows who else is doing what they are doing, but they are still being able to provide this assistance. And also, ideally, we want to achieve near Oracle performance in the sense that the performance is as good as pulling the data together. So this is going to be a luxury that we need to verify case by case under some mathematical assumptions. So there is a closely related literature that I briefly mentioned about federated learning. So federated learning is a recent framework where the goal is different. The goal here is to leverage resources of edge devices, like smart devices with low computational power, to achieve a global objective. So there will be a central controller that controls everything, and there will be a transparent global model that every entity and every device will share. And there is some recent work that is about heterogeneous personalized federated learning. And we also have some work there, but I'm not going to talk too much detail. So the fundamental difference here is that we consider more about this personalization and also the privacy of not only data, but also models and objectives. So next I will talk about modeling methods, different methods. So the original problem we studied was to come up with the information to exchange in assisted learning. So in many other settings, like federated learning settings or other distributed learning settings, it's typical to assume a global model. So it's relatively understandable to share or average over parameters from different devices because the parameter is the same parameter among all the learning agents. But in the assisted learning setting, there is no global model, typically no global model. And it seems not trivial what is a unified method. So we consider different scenarios, different potential techniques. The first, these include the transmission of fitted residuals or sample coefficients or neural coefficients in the setting of deep learning. And today I will mention some of them and I will just highlight the insight of them. So I will start with this vanilla version, which is our very first work on this assisted learning. So in this version, we studied regression, where B is going to help A with A's regression learning task. So remember, A here has a model data, B has model and data. And suppose A has a task label YA, that is a regression label or regression response. That is not going to be shared because we want this to be private. This is the objective. So what is going to be the temperature tomorrow? And what A does is to fit a local model that is denoted by A1. So A uses private model, private data, and private label to fit a model, and then calculate the residual of it. And then A will pass this residual to B. So this residual typically doesn't contain the original information, like temperature. We don't know what it is. It's just going to be something around 0. And then B will use this residual as a task label. So B will treat this residual as its local regression label and use its data and a model to come up with a regression model denoted by B1. So B1 is a local model. locally privately stored by B. And then B will calculate the residual of this learning task. That's called residual 2. So this residual is not the previous one. It's you can think it as the residual of the residual here. And then B will send this local residual back to A. And A will initialize the second round of learning. A will treat this new residual as a local label and continues this procedure. And we continue this procedure until some stop criteria is triggered. I will mention that later. But for now, we can think that the validation error no longer decreases if they have some preserved validation data set. So that is the training stage. So stage 2 here is the prediction stage. Now there is a new data coming in. So for example, A is an insurance company and B is an ice cream shop. And now there is a new customer who is observed by both A and B, suppose. And then A will evaluate the data, what it observes, using all its local models, A1, A2, and so on, and add them up. So add the prediction up. And then B, so does B. So A will need B's part. B will send what it calculated to A, and then A aggregates them. So A will aggregate what is sent from B to come up with a final prediction. And in some cases, we prove that A can, in this way, A can perform as well as if data was centralized, which can be thought as an Oracle benchmark here. So in this slide, I will illustrate the technical insight, so why it works. And I will use this simple linear regression example. So suppose that A and B use linear regression models. So in the learning stage, what happened is that A will first project the task label YA to the orthogonal space of its local data XA. And then the orthogonal projection is a residual sent to B, which is then projected again using B's local data. So this projection happens several times until it eventually converges to the projection onto the joint space of A and B. So it can be proved that this will converge. And consequently, A is as if doing this joint projection onto the pooled data, centralized data from A and B, but without actually transmitting the data. And the prediction stage is essentially mimicking what A would do using the trend model from the centralized data. Because every time we are fitting this residual, so at the end we just aggregate them. So this is the prediction stage. And in reality, B will help A for every new future data in the prediction stage. So A will continuously need B's help. And the interpretation, as a quick summary, is to iteratively send the garbage, which each of them think as garbage locally, to the other side, who will then digest the new information from it, and then iterate until they digest enough information from it. So this is an example. And next, I will talk about different extensions of the vanilla version of this assisted learning. So the first motivating question is, how do we perform parallel tasking, where A and B simultaneously help each other? So previously we mentioned B help A. How about A help B? And how about they help each other together? And second, I will mention about extensions to different tasks, say classification. And then I will talk about this question of how to theoretically and practically understand the limit of learning. What is the best possible results they could theoretically and practically achieve? And also, how do we defend against adversarial entities if B is if B is some entity that is adversarially stealing information from A? How does A trade off the privacy and information gain from it? So first I will talk about some idea, Pareto assisted learning, where this Pareto here is named the reason we name Pareto is from this motivation from this concept of Pareto efficiency in economics. So this describes a situation where everyone is happy. It's a win-win situation. So currently A is happy if B helps A. So how about we also let A help B? So a straightforward solution is to run two different assisted learnings. So first time B help A, second time A help B. So there is a potential problem here in practice. That is when A is not very cooperative. So what if B help A in the training stage, but A doesn't help B? So another relatively straightforward solution is to consider stopping the collaboration. So if B help A in the training, but A doesn't help, then B will stop helping A in the prediction stage. But this is not ideal because in practice, they would have already started the collaboration, and it is resource consuming. It's not a good mechanism design, basically. So we want to have a mechanism design that binds the entities together. So each of them will have to assist others while it is being assisted. So we want a win-win solution. So I will give a high-level idea of how this can be achieved. So still going back to the previous illustration. So A will train a local model and come up with a residual and send to B. But B, before its local training, will privately inject its own task label. So here, for example, we inject tau B, some constant, tau B, times what B is truly interested in, YB. So what B is really doing is to not learn what is sent from A, but a mixture of what is sent from A and what B is truly interested in. And in general, A will do so as well for the round when B initializes and sends to A. And then A and B will need to jointly decode during the prediction stage. So in the training stage, they will train something that is not what they truly want. It's like a compromised, mixed label, but they need to decode it during the prediction stage. And it doesn't do good to any of them if any of them does not collaborate. So I will explain the idea in this slide. So briefly speaking, what happened is that if B, let's say Bob, injects its label YB multiplied by constant tau B, the targeted model is approximately YA plus tau B YB. And similarly, for the round, when a round is initialized by Bob, A, say Alice, will inject her objective to make the target approximately YB plus tau A YA. So each time they are doing a different task, that is not what any of them wants, but it's a linear combination of what they want. So in the prediction stage, if they are going to collaborate and well predict Y delta and YB delta, they could theoretically decode using a linear combination of them. So this is a rough idea. So here I show a real data experiment where we consider this medical benchmark data that is naturally divided into different divisions, different tables. So they are collected from a hospital system in Boston, and they have different clinical divisions. Each of them has private data, and the data can be linked by patient IDs. In this particular setting, we considered about 7,000 patients, 16 variables after some pre-processing. And there are two clinics, and one is interested in predicting blood pressure. A second is interested in predicting the length of stay. And they are going to simultaneously assist each other. And in this particular experiment, we consider the cross-validation, which I'm going to talk a little bit more. So basically they preserve some of the data as validation data so that they know when to stop. When it no longer helps, they could stop. Okay, so here is the table. So the column here, different columns here, 2, 8, 14 shows different number of variables that entity A has. So we just divided the 16 variables in different possibilities, 3 different possibilities to show that, to illustrate when the entity A has more information to help or has less information to help, what will happen to their performance. And different rows here means what if A and B do not collaborate, or they collaborate, but with different tau A, tau B. So the take-home message from this table is that, first of all, the Pareto-assisted learning will often significantly improve over single entity learning. As we can see, for example, this 15, much larger than 12, considering the standard error here. And the second is that the performance depends on the number of variables offered by the other entity. So if A is more powerful, more informative than B, then A could actually help B more than B helps A. And and last, it is the performance is not very sensitive to the choice of the constants tau A, tau B. And here are some simulated data experiments. So we consider a simple setting where A and B have linear models. And this figure visualizes what happens if they assist each other at different rounds. So at the beginning, A's performance is just its local performance because it doesn't get any help from B, and so does B. And as time goes on, after 9 iterations, 9 rounds of assistance, both of them will become better, and eventually, as very close to the oracle performance, as if they use the centralized data. And here is just snapshots that show their predicted value y hat versus the true underlying mean value, expectation y. We can see that they get sharper and sharper 45-degree lines. A second extension is about other possibilities, not sharing the residual, what we can share. So the idea is about confidence passing. So for example, suppose we have two cameras and they observe the same objects, same dogs and cats in different angles. So in the first image, A observes it's a dog, so it can quickly identify with high confidence that it is a dog and tells B. And B doesn't need to do anything. B knows that A has done a good job. In the second image, A is not doing a good job. So A tells B, this is not something I'm sure about. So B will learn this image, but B will learn this counterpart in its locality. So B will learn the corresponding image it observes, and then tells A, I'm sure it is something. So B can tell A that I'm sure it is something. And so A knows that B is able to help in the future. So this is confidence passing. Basically, they pass the confidence. And this percentage basically shows our accuracy improvement after actually 2 rounds here. And I will give a high-level idea of how we formulated this. But before that, I will illustrate the main idea visually. So the main idea is that A will train with the weight, sample weights W. W here encodes the confidence associated with each image. And then A will send the confidence to B so that B knows what A is not sure about. And then B focus more on what A is not sure about. And eventually they will iterate this procedure. Suppose we have more than 2 agents, we have multiple agents. Every time they just share with each other what is their model confidence, how good I am using my local model, but I don't tell what is the model I'm using. And also the object confidence, how good I am doing prediction for each object. So technically speaking, we derived what is going to be shared by formulating the following supervised learning problem. We consider the function class that maps from the data to the label in the following form. So each of them has a private data. We assume it can be expressed as a summation, weighted summation of individual models, local models, evaluated at local data. But this model and these weighting coefficients are going to be learned on the fly as they communicate. And we use the exponential loss. And the idea here is to use this loss so that we can decompose the optimization problem that is in hindsight to something we can actually operate on, because we cannot really share data. So if we use this carefully chosen loss function, we can actually decompose it, because e to the power of additive becomes multiplicative. So they can basically do this local training by sharing some kind of weights instead of this actual data. So here is a illustration using images. We consider 2 data sets, and A holds quarter of the picture, B holds the rest. And without the help from B, this ASCII is our method. Without the help, we have a single performance that is not as good as with help in both of the data sets. Although we are not doing the near oracle performance, but it's already pretty good, especially that here we only have 2 rounds of assistance. So after only 2 rounds of exchanging the confidence, we can significantly improve the single learner performance. And also the last row is also interesting. So I mentioned about the setting where we have cameras who do not want to transmit raw images, also due to communication bandwidth. So we calculated the transmission cost in bits. We saved actually over 1,000 times computation in doing this collaborative learning. We don't, because we didn't require the transmission of raw data. So next I will briefly mention the limit of learning. So we will study, first of all, how to quantify the best achievable results. So in a recent work, we developed a notion of efficiency of learning. So this efficiency of learning describes what we can theoretically achieve if we are going to select the optimal model from a set of candidates. And the definition is actually straightforward. I will explain. So the idea is that the denominator is the minimization over all the possible performance offered by all the possible models, or in our case, collaborations. And the numerator is what is selected. So we want the predictive loss to be as close as the best. So the ratio goes to 1. So this is actually much stronger than classical standard statistical learning theory results, because we are not only bounding the outsample loss, we are also requiring the ratio to converge to 1. And does it exist any method that we can achieve this? So we showed that it is achievable by theoretical construction. I mean, it's a construction, but it's a realistic construction, but we just need some theoretical assumptions to guarantee this convergence. So in reality, how do we efficiently, practically approximate such a oracle result? So the second focus here is to have this correct way of doing cross-validation. So cross-validation is widely used and is very natural consideration in our setting. So we just reserve some validation data. But how many data do we validate? How many data do we cross out? So this is actually a very fundamental problem. And we have many choices in our packages, like leave 1 out, 10-fold, 5-fold, and half-half. So our general results say that, first of all, to achieve good predictive model or agent from candidates. So basically to achieve good prediction results, we'd better use leave 1 out or leave few out. And second, to fairly compare the performance of 2 models or agents, just to compare them instead of doing a good predictive work, we probably prefer half-half. So these are all theoretically founded and practically verified through different experiments. And a third related problem is, how does an entity know that it has already achieved the best possible results? Practically, how does it know? So that doesn't need to pay for further service. So we develop, our goal is to develop interpretable machine learning here that not only knows whether it is good, but also knows why it is good or why it is bad. So the main idea of the first direction is to develop a goodness of fit test to test whether the model is adequate to this particular observed data set. So the main idea is this: we have a data set and we learn a statistical model. That is a generative model. And then we generate fake data from the learned model. And then do a hypothesis testing to test the similarity between these 2 data sets, the original data we observed and we learned, and the fake data that we generated. And how do we know if it is rejected? If the hypothesis that the method is good is rejected, we also want to know why it is rejected, why it fails. So here in this particular example, I showed a very simple neural network that didn't do a good job in MNIST dataset. So we want to understand why it fails. So we use our method to visualize the variables that are inadequate in explaining the similarity between these two data sets. So basically, we just find out the dimensions that caused the rejection of the hypothesis and visualize it. We can see it is understandable that this is the main feature, main difference between two classes of clothes here. And the last extension, which I will briefly mention due to time constraint, is about this adversarial learning scenario. When we have A and B helps A, but B may have a second purpose to steal some information from A. So the key idea is that we studied this black box setting where the information exchange from A to other entities is modeled as information channel, where we have query input and response output. And this information channel is described by a kernel K star here. And without any security measure, we just expose this channel to the public. But this is not ideal because if in case B is adversarial, this channel K star, a model, private model, could be hacked easily. So what we did is to consider the cascade channel, where we studied two information channels, K1 and K2, before and after the K star. So what is exposed to the public is a cascade channel K, that is a concatenation of K1, K star, and K2. And the problem now is to design K1 and K2 so that it doesn't compromise the utility. That is here we model as KL divergence between these two channels, average KL divergence, and also the information distortion due to the K1 and the K2. So we studied, we proposed a principle called the information laundering principle, where we launder the information in a proper way by designing K1 and K2, by optimizing this objective. That is a trade-off between utility and privacy. So I will conclude the talk with a quick summary. So we mentioned this assisted learning as a general way to perform privacy-sensitive collaborative learning, particularly in the setting where entities or people have private data models or tasks. And these methods are mostly built on protocols where they exchange set information, statistics calculated from the data. And there are different generalizations, some of which I mentioned, and some of which I listed here. So some other exciting research directions include this question of what if an entity has data, but not model or computation? So we imagine that this entity has to outsource the data to others in a proper way. And the second is to evaluate the privacy using a data privacy framework. So I didn't mention, but we have work here to further enhance the privacy using some framework such as differential privacy. So the basic idea is just to inject more noise into whatever is transmitted. And the third idea is to decide the best order of assistance in the presence of different entities, in multiple millions, potentially millions entities. And the last is to study the setting where we have the same attributes, but heterogeneous data. So this is still ongoing work with E. And we have some very exciting discoveries. So I will conclude the talk with some references, and thank you very much for attending my talk.
Okay.
Thanks. Thank you, Jie.
Thank you, Yi and Yu.
Yeah, it's a great talk. So we do have a couple of minutes for questions. So is there any questions from the audience? You can, I think you can unmute now and ask questions if you want. Yeah, so maybe I can go for the first question. So Jie, when you talk about there's a residual passing algorithm that you described for the basic assisted learning setting.
Yeah.
And you mentioned that after the assisted training part, in the second prediction stage, the agent A still needs some assistance from B in order to make a good prediction. So is that a desired thing in the assisted learning scenario, or will that introduce additional cost?
Sorry, can you hear me? I think I got stuck somewhere.
Okay, can you hear me now?
Yeah, I can hear, but I cannot see. Let me see.
Okay.
Yeah, maybe it's fine.
It looks like his video is frozen, but everything else seems to be working.
Yeah, maybe I just talk. Yeah, it's a great question. So currently, in our setting, we studied, we supposed that A will need B's persistent assistance during the prediction stage. The reason is that B has local models never shared. So B has to send what is calculated from those models and send to A.
Okay. Oh, I see. Yeah.
Yeah. Yeah, I'm not sure whether it's good or bad. I mean, if A constantly depends on B. Maybe it depends on the specific scenario.
Yeah, in that case, if the model is not shared, then
yeah,
that has to be the case. Yeah. Okay. So any other questions from the audience?
So Jay, so you talk about the confidence passing approach, right? So,
yeah.
And when you talk about the residual passing approach, you talk about, I mean, after multiple rounds, it's going to converge to the Oracle case. But for the confidence passing case, you only talk about 2 rounds. I'm just wondering what happens if they are allowed to do multiple rounds.
Yeah, thank you for a great question. Mm-hmm. So first of all, the confidence parsing was originally motivated to solve this classification problem. Mm-hmm. When the regression parsing in general doesn't work. So for the classification task, the label is going to be classification label, and we can use residual parsing if we put it in a numerical embedding. Actually, we theoretically proved that it is correct to do so. Just use 0, 1 or 0, 1, 2, 3 numerical embedding for generalized linear models. But it may not work for more general models like neural network models. Mm-hmm. So currently we think that this confidence parsing is more general, mm-hmm. in the sense that it can actually work for both classification and regression, mm-hmm. Because it really it only requires the transmission of confidence.
Mm-hmm. I see.
Yeah, thank you very much.
Yeah, and another quick question is, so in your talk, right, when you talk about privacy, so it's it refers to the case when the raw data or model is not transmitted. If that's the case, you call it private. Is that
yeah, current setting, we hope that we suppose the data, model, and the objective are all not transmitted.
Mm-hmm, mm-hmm. I see. Yeah. Thank you. Yeah. Great talk.
Yeah. So we have a question from the audience. So the question is, how will different organizations start using or be encouraged to use this more private data collaboration framework?
Sorry, can you say it again? optimization methods.
So okay, can you see the chat window? I can say it again. So
Actually, I got stuck here, so I cannot see.
oh, okay. So the question is, how will different organizations or entities
Okay.
start to use this assisted learning type of data collaboration framework?
So yeah, this is actually what I have been thinking every day. This is a very important question. So how do we encourage them to use this? Yeah, I think at this moment we are still in a stage of developing techniques, and we probably need to work with some organizations that already have infrastructure and also incentive to work with other entities. So yeah, I think this is more about commercialization or yeah, I think it's a great question, but I have no answer for now.
Great. So I do have another maybe a very interesting question. Maybe it's not even a question. It's just something that pop up into my mind.
Okay.
So imagine that suppose this framework is commercialized and many users are using this assisted learning framework. So basically they purchase this service from some service providers, for example, Amazon in the future, let's say.
Okay.
So then among these users, let's say maybe two of the users, they are actually competitors. They are competing in some field.
Right.
And both of them purchase a service from the same service provider. So actually the service provider will have the control to, maybe depending on how much each of the user pays, they will maybe control the amount of service.
That's an excellent point.
Yeah.
Actually, this is the reason that I prefer not to have centralized service. So
Okay.
I prefer decentralized way. Like we can have a platform, we can still have a platform, but there will be no supervisor that allocate the resources. It's better that we have this mechanism design that let A and B assist. So for example, in the Pareto assisted learning I mentioned, actually we can already achieve a preliminary version of what you described, say A and B. A is much more resourceful than B. But A doesn't know what B can offer before the assistance. So how can we have a fair mechanism that B gets whatever is offered to others? So if B is not that good, it will not receive enough from the others. So currently, so that's actually one of the motivations that we have this parallel tasking. So they mix together. And then once someone stops, sees that it's not a very encouraging result, then it stops, say A stops. Then B will have no further gain. They will just stop simultaneously.
Yeah, thanks. That's very, very good clarification.
Yeah, thank you. Yeah, but for comprehensive study, I think it definitely requires many more interesting work.
Yes. So do you have other questions from the audience? Okay. So if there's no questions, so let's So let's thank the speaker again. Thank you, Jie, for coming today.
Yeah, thank you. Thank you again.
My pleasure.
Thanks.
Meet you. Yeah.
Thank you, Jay.